Short-term demand forecasting. Operations and planning is based on inventory and production theory in all industries, most especially so with electric energy. The amount of coal to have on hand, the amount of gas to have available, and the equipment to be in place to provide reliable production continuously at the desired level of reliability requires that the forecast be correct sufficiently to handle all of the impacts of what future demand may be there. Inventory theory is based on storage policies and strategies, and they're based on the objectives of supply subject to transportation constraints, production capabilities, and expected demand. Inventory policies are dependent upon some forecast of the demand, given the present and future prices of resources and the present and future prices of electricity as an energy resource. So the idea of forecasting is to get the right amount in place just in time to provide the services that are needed. The forecast is an essential part of this process. It is the first step of this process. Other industries where forecasting plays a critical role include any firm that has to market consumer products, financial planning, and any service industry. Also, companies must be able to forecast what other companies need to provide the required inventory of products for other industries to make their profit, either as finished goods or as services. So the idea here is we're going to have the start of the process of finding the optimal policy, how much can be sold, how much will be consumed, and therefore what equipment must be available and what capabilities of transport has to be available. Now, forecasting is one of the most general or most applied operations research topic. It is also very widely used as an economic input for economic forecast, and also in terms of working with the various markets where commodities are bought and sold, as well as financial instruments. Predictions of future events and conditions are called forecast, and the act of making such prediction is called forecasting. It's a key element for all decision making. The main thing we wish to do with forecasting is to reduce the risk in strategies and decision making, because we want to reduce the unexpected profit or cost. In the most general of terms, demand forecasting is categorized into various categories. The perspective we're going to have here is that we're going to be applying analytic methods. Many long-term forecasts are more subject to those who have to deal with technology changes, which are harder to predict. The analytic methods we will be using assume that history will repeat itself and that past demand can be used to forecast the future. As we use each of these analytic methods, we will have to determine the error in the forecast. First thing of every forecasting step is to identify the size and scope of the system and the type of system to be used. That is the type of equations to be used. One of the main things we have to do in terms of forecasting is decide if we will do a time series or an econometric forecast. And we'll get into this more in a few more minutes. Once we've identified the system, that is the equations to be used for forecasting, we then have to use another technique to estimate the parameters for those equations. After all, fuel scheduling is going to be slightly different than coal scheduling when we're talking about oil or natural gas. And what we wish to do is to achieve the best mix of resources to minimize the cost and to make best use of the equipment that is available whenever it is available. Depending upon the forecast of production, the next program that we always think of working with is unit commitment or unit scheduling. Or in terms of markets, it is how do we purchase or sell the commodities on the various electric markets, such as electric energy, energy imbalance, spinning reserve, ready reserve, and in the near future, the amount of inertia that is available. What we're going to do with this chapter is we're going to look at time series for the most part. We are not going to be looking at econometric other than to mention what the differences are. Econometric forecast is forecasting based upon the economic conditions. We go down to essentially the grassroots, if you will, of looking at our customers and what are the economic drivers that they respond to consume electric energy. These are both statistical techniques. The time series is more general because we do not look at these driving factors, whereas econometric analysis looks at the driving forces to consume electricity. So they're both random variables. They both will use probability or stochastic processes. And the main difference is the amount of work and the amount of data needed. Econometric forecasting will typically go from the end-use customer, the residents, the commercial or the factory industry involved, and determine what is their activity going to be. When we look at homes, we have to look at the appliances that are used, which are the dominant appliances, such as refrigeration or air conditioning, and which of them are going to be used more as the economic health of the area increases or decreases. One of the interesting things is that we still have to be aware of future conditions, even when we're doing time series. The one thing that everybody knows is that history does not always repeat itself, and there are technology changes that require us to alter our forecast and to look at time series either in a more component fashion, and one of these could be, or is expected to be by me at least, is demand response. Demand response is one of those self-rewarding economic drivers that is new, therefore we don't have that much information on it, but very widely accepted that it would change the demand. And one of these forces that is coming about now is the area of transactive energy, where the end user can buy and sell contracts as well as ancillary services to meet their objectives. It is not expected that every house will start forecasting spinning reserve to sell their demand for spinning reserve, but there is the very solid concept that there will be some kind of pooling agent that will pool households together and will react just as some of the large companies do, like Alcoa, DuPont, and Dow, and that they will respond to price incentives when the system needs more energy than was scheduled, or when the change in energy needed varies quickly. Automatic generation control is a package that has been tracked over the years, and it inherently matches the demand and the supply instantaneously. The first response of the power system is to change the power output of a generator by converting the rotational mass energy, the inertia, into electricity as the demand increases. Once that is sensed, the governor opens the valve more for more energy to be input into the power plant system to produce more electricity. And centralized AGC is used to control these responses so that the frequency returns to the scheduled value. In the US, it's 60 hertz. In other places, it's 50. But here again is another place where forecasting on a very short-term basis is an active area of research and widely needed. Economic dispatch is another area. But let's go back to time series. What kind of time series analysis can we do? There's many. The most traditional is some kind of filtering technique. For those students who have taken courses on signal processing and control theory, you know that many controllers use exponential or double exponential smoothing to determine what the change is required or desired to be to keep a system functioning. The next level up from filtering is the more very traditional Fourier or waveform analysis, whether it be by Fourier transforms, Hartley transform, or wavelets, to determine the periodic signals that are present in the time series. We will introduce in this course one thing you have probably not been exposed to, and that is autoregressive and moving average forecasting techniques that decompose the time series into two other components, which you have probably not heard of. Those two techniques can be converted to state space techniques, such as you would find in your modern control theory course, especially common filtering, and we will finish the course discussing common filtering. The area of artificial intelligence, or computer intelligence, has been very active in trying to determine how those techniques could be used for forecasting. Artificial neural networks has achieved considerable success, especially as noted by the EPRI application called HELMS, the Hourly Electric Forecasting Package. This uses an artificial neural network, which is a nonlinear curve fitting technique, in essence, that allows us to break the time series into other components and then use that to forecast the future. As we go along, we will talk more and more about the applications and how forecasting is required for each of them and what changes are needed in the techniques to satisfy the correct input data for these applications. The time frame for the text we are using is going to be operations. We can frame forecasting as either long-term, 1 to 10 years, typically found with capital budgeting and system planning. Almost all industries require this. Electric utilities, of course, require this because it takes many years to build a centralized power plant. It also takes many years to transition from one type of resource that is used to another. Capital budgeting at present is struggling to define how to integrate solar and wind generation into the overall process to provide reliable and economically efficient electricity. Another area for long-term forecasting is contract evaluation, whether it be for fuel contracts, interchange contracts between companies or exchanges, and the use of hydro, longer-term storage projects. Hydro has a major input on every continent, most specifically in South America with the Brazilian project, in China, and even in the US and Canada. Canada is predominantly hydro, and they optimize their hydro to sell as much as they can and to provide as reliable service as they can, subject to the limitations of how the water can flow. Of course, the main user in the US of such optimization techniques is the Bonneville Power Administration hydro scheduling package. The midterm time frame for forecasting, that is 1 to 3 years, is primarily centered around maintenance scheduling. When do we take a unit out of service for upgrade, for refurbishment, or for conversion from one fuel to another? Another midterm is fuel scheduling, such as nuclear fuel. When can we take the nuclear unit out for a prolonged period of time to either cycle or to replace the fuel rods? Fuel contracts, especially take or pay fuel contracts, are very important when you want to match up the gas, oil resources with the demand of electric energy. Again, fuel scheduling can also be thought of as hydro scheduling when we think of the hydro facilities that have 1 to 3 year cycle capability and how do they respond. Short-term time frame deals with unit commitment and markets for electricity. These are normally dealing with tomorrow's demand, especially when you have daily markets for energy sales. And in traditional use, they would schedule energy for the next 7 to 14 days to make use of pumped hydro storage or other storage capabilities. Batteries, of course, are coming up to be a major source of energy storage capability, as well as flywheels for instantaneous response to changes. Fuel contracts are critical in the next 7 to 14 days, and it's not uncommon for an electric utility to buy and sell fuel in the next 14 days instead of producing electricity if it is more profitable and they have overbought their fuel. Of course, if they've underbought, what they must do is decide how much fuel to buy to maintain reliability without getting into much risk of having to go to interchange contracts. So our work in this text is primarily in the unit commitment area and the maintenance scheduling area for the next 14 days, although we can stretch this out to the next year for operational planning. So the immediate use, we've already talked about AGC, but also in a 5-minute to 24-hour period, we have to worry about economic dispatch. What are the future demands to be, especially when we get into valve point loading? We want to go through the valve point change only once a day. So those forecasts are needed for the next 5 minutes to 24 hours. Security constrained economic dispatch requires forecasting, so we move in a unified direction, either in increasing or decreasing, as well as security constrained unit commitment or optimum power flow, another application of renewed interest, to match the demand with the supply with the proper amount of resources available. The energy markets, of course, bring another need for forecasting. What kind of bids, what kind of offers in terms of bids and asks, buys and sells do we do on the market for tomorrow, or for within the hour for the energy imbalance market, or within the hour for any kind of reserve markets, or for the inertia markets that people are seeing coming about. In addition, we need forecasts to handle the hedges, commodity hedges for fuels, electric energy, and ancillary services that grow up into a competitive framework. So the framing of this section is we're going to focus on traditional short-term demand forecast. Hourly for the next 7 days are 168 hours. That can be extended to immediate use, such as the next hour. And it can be applied to most of the markets that are existing in the competitive marketplace in terms of the energy day-ahead market, the energy imbalance market, spinning reserves, as well as the inertia markets, and any other ancillary services, including reactive power. Almost all of this work with time series deals with pattern analysis, pattern recognition, and therefore parameter estimation. We will not be dealing, as stated, with econometric forecasting because of the very different approach to the data that is required and how it is assembled. However, the smart meter projects start to force us to consider econometric forecasting, or at least a time series analysis for those devices that could be under control under various smart meter programs, such as air conditioning, which was used in Florida in the mid-70s due to the oil embargo to maintain a cap on the price of electricity. Energy storage has become the hottest topic as of late. Pumped hydro has been used for several decades. Batteries are now being used, especially the Tesla battery is of extreme use, we hope, with solar and wind generation. Gas turbines allow us to convert electricity into gas by not using the gas turbine and therefore saving the gas for a future time period. And therefore we can convert electric energy into gas. Another area with transactive energy that is very interesting and appropriate right now is demand response, where the end-use customers could be pulled that their heavy use appliances, such as air conditioners, most importantly, and refrigeration, could be turned off when the system is in stress, such as frequency deviations or voltage deviations, and therefore enable the system to remain stable. And it is this area that I have been most interested in for at least 2 decades. The whole goal of energy storage is to reduce the demand at the peak and move it to the off-peak period or to a lower period where the costs are less and the capability is still there. So we want to reduce the peak at least. Now this is something we don't like to do in electric energy. When you reduce the peak without moving the demand to another period, is you have lost income. And this is why many demand response programs are not desired, because they reduce the end use of electric energy, which is not a goal for either the utility or for most consumers. So when we talk about demand, what are we talking about? We're talking about the end use. We're going to forecast the energy demand as being the electric energy and services used at the customer site. We are not going to include the losses of the transmission and distribution system, as these can vary depending upon the equipment configurations. We're not going to do forecasting of facility services, but the techniques we're using can be extended to those. We are going to talk a little bit about forecasting market prices, especially the clearing price, because of the deregulation of electric energy across the U.S. being at least halfway along. And therefore, you must be able to understand how to forecast the markets for electric energy, including ancillary services. One of the main things we have to decide, is this a random variable? In other words, can we do a probability analysis or a stochastic process analysis? We will stay primarily with random variable at this point in time, where we can use probability theory to handle the uncertainty in the future. Probability demand is random to a certain extent. We don't know when everybody's going to use their appliances. Unless it's extremely hot, then we know all of the air conditioners will be on, or extremely cold and all the heaters will be on. And therefore, we have to look mainly at weather dependent devices, heating or cooling. TV and internet use can become critical when there are very popular events where all of the TVs are turned on at the same time and everybody is synchronized to the TV schedule. Commercial demand is less random. Commercial demand is customer-centered on the workday. Cleaning facilities and other facilities that use a lot of energy, grocery stores, are governed by the workday cycle of their clients and their hours of operation. So therefore, they're slightly different in terms of time series analysis. We must take into account those workday dependencies or the working hour dependencies. Industrial demand is almost deterministic. Scheduling of production facilities is done into the future to make sure the workforce is there and that their supply resources are there to produce the product or the services. There are a couple of cases where this is not as true as it used to be, especially for those companies that have their own generation, such as Alcoa, DuPont, and Dow, who have their own facilities to generate electricity. Companies like Alcoa make decisions 5 minutes before the hour as to what they will produce. Will they produce aluminum, something that is easily stockpiled or bought from other companies, and electricity, something that has to be produced immediately and delivered immediately. And they will decide, based upon the bottom line profitability, which to do. It is not uncommon for Alcoa to turn their plants on or off, depending upon the market price of electricity. So for those facilities, we have to be very careful to include those capabilities, and therefore the time series have to be converted to other components, such as whether they are in standby mode, they have shut down, or they are in full production of the product that they are making. What is a random variable? A random variable is a variable that can take on any value within a certain distribution. Doesn't mean it's limited to be no change, but the amount of change is given by some kind of distribution, such as a Gaussian distribution, Poisson, etc. This is also true for various resources that are available. Wind is a very interesting supply source to forecast and is very critical when integrating wind generation with traditional fossil fuel and other units. Sunlight is another random variable. Not because the sun will not be there, but because of the cloud cover that is there and how thick the clouds are and what is the spectrum of light that the solar cells respond to. Stochastic processes are primarily used in financial markets. This is when we have a understandable math equation that has fitted the random walk theory of any market, as well as the amount of change that can take place given the economic drivers for that particular commodity, or for that matter, for stock price. Most of these are mean reverting. That is, they deviate from the expected value and then get back to it. Or they have some other statistical attribute that we can use to model these markets with the appropriate math components. Financial markets are stochastic processes, mean reverting, arch, garch, and other techniques are used for these, as well as econometric, of course. All financial markets are based upon the economic of the industry that's being studied, of the society we are looking at, how they use energy, and therefore can be more of a grassroots building than the time series allow. Of course, economic could also include the global impact of gas prices, of gas availability, as well as oil or gasoline availability. So there's many things we can do in forecasting that is not covered in this chapter. The categories we're going to look at is qualitative first, very quickly. The expert that has always done well in forecasting demand is a senior operator or a market analyst, somebody who has done this for many years. On-the-job training provides a very large body of knowledge to work with. This is often called the Delphi opinion or the Delphi technique. Delphi being the oracle who knows all and can see the future. This chapter will deal primarily with quantitative techniques dealing with time series, whether we use linear or nonlinear regression, filtering by Fourier transform are eventually common, And of course, there's many other transformers that can be used. The Hartley is of interest to me, as well as to many others, because of the fast Fourier and fast Hartley transform techniques. In time series analysis of control theory, especially with the Box and Jenkins text some years ago, ARMA and ARIMA processes, which are a breakthrough into state space techniques eventually, have been very widely used successfully in production cycles as well as electric energy. And as noted, the new computational intelligence, such as artificial neural networks, are a very good curve fitting, and indeed are a nonlinear curve fitting technique that has seen success. Let's talk a little bit about Kata Metric and what we're going to not include explicitly. Number one thing about econometric is unemployment is not included. If a factory has a shutdown or a layoff or a temporary conversion where the employees are not working, the amount of demand in an area will decrease significantly. Weather has an extreme impact on the electric demand. As it gets hotter or colder, more energy is needed to make our homes habitable. Also, sociologic changes such as green trending show that in behavioral economic sense that people wish to use more green products than traditional fossil fuel products. And we must include these, and we can do this a little bit by time series, but not as thoroughly as econometric techniques can do. So what we remember is the demand for any and all products is a result of a need. That is the cause. Behavioral economics can often tell us what the individual will do with their budgets, what they will fit into their budgets, what they will exclude. The industrial mix will tell us how much we need to look at factories and their production schedules and how those are changing. And of course, the commercial mix is what goes in between. The industrial, where most of the money is generated for individuals to use, which they then spend through commercial services as well as for the home services that they need to live in our present world and weather economy. So the applications we talked about are scheduling of thermal units, especially the fossil fueled and nuclear units, hydro units in terms of the amount of water that is available or snow, pumped hydro in terms of what we can store because we have excess generation at certain periods, particularly the midnight to 6 a.m. period, and we need that extra generation in a on-peak period. Energy storage is also used for the new solar and wind generation, but also because it provides us with our reliability factor, if you will, of providing electricity at the right point in time. Demand response we've talked about, and I think the user should look at transactive energy as one of the major technological changes that is facing the industry and could alter the forecasting techniques that are used and successful in our field. Contract negotiation is what transactions interchange and transactive energy is all dealing with. Although we do quite a bit of transaction or contract management right now with our independent system operators and power pools. One step ahead forecasts are needed for AGC so we can have the right units positioned to respond to increases or decreases of demand as are expected over the next 5, 15, or 30 minutes. In the next 24 hours, we'll do scheduling of transmission and generation to provide the correct security, a minimum level of reliability, that is. We'll do unit energy scheduling so we can reduce the cost as much as possible. We'll provide the proper ancillary service through the various markets at the right point in time so that when things go wrong, the system stays running and functioning. The energy imbalance markets that are now evolving will allow us to take care of the forecast errors and the equipment outages that could occur on an hourly or smaller basis, such as 5 minutes in New Zealand and Australia, because they have a 5-minute energy market. And we need to rebalance the resources when things go wrong. Maintenance schedules are critical everywhere. As the operator states, there's always something that is outaged. It is never the fact that everything is there or always there. And therefore you must look at the maintenance schedules and schedule equipment repairs and unforeseen outages to maintain the proper level of supply that can reach the customer, can be transported to the customer. One of the things we'll talk about briefly at the end is bus demand forecast. If we're going to do a power flow for 2 days from now at 3 o'clock in the afternoon, we have to have a good idea as to what is the demand going to be at every bus in the power flow. It doesn't matter how feeders are switched from one bus to another, as happens in operations, or what the transformer taps are, is we have to be able to include those factors into our forecast so that we can do the proper maintenance and outage scheduling in the future. We're going to be working with an additive equation for the most part. Component integration of these various factors is what we'll be looking at. So we'll separate the forecast into a base amount that is always there, a weekly amount that changes per day and hour of the week, a seasonal amount that will vary depending upon the season of the year, fall, winter, spring, summer, as well as whether the day in question is a weekend or weekday or middle of the week. We will even call those changes seasonal changes, as is traditionally done. And of course, our whole goal here is to reduce so that the noise that's left over is as small as possible. An alternative is multiplicative modeling that has had some success, but is primarily the additive, and due to time and space limitations, we will be dealing only with the additive component integration approach. Hourly system demand forecast for the next 72 to 168 hours. We first take the time series and determine what is the base load. The easiest way to do that is look at what is the mean. That is, what is the base load always there? It could be the mean, it could be the minimum demand, and therefore we look at the rest of the demand as a time series, in this case y hat here, that we will apply further analysis to. The part that is always there, which could be in itself based upon season, or month if you will, is constant. Once we identify and remove that, we then look at the remaining part of the time series and determine what does it look like in terms of previous values of demand and previous values of noise, W. As is traditional with many books in forecasting, we will be introducing noise as either N or W. W primarily when we wish to use that noise in the forecast parameters or components. The hourly bus demand forecast will take the demand for the system, separate out somehow by a ratio, if you will, and therefore we can come up with the demand at each and every bus. This is the most trivial of calculation methods used. We could also identify at every bus what kind of demand is based there, and then the rest could be forecast from the system demand, or we can also break it out into other components in terms of residential, commercial, or industrial, which means we can start to mix some econometric in a very limited fashion with time series analysis. So what are the interesting extensions for these tools? What happens when we switch a feeder from one bus to another to maintain the voltage on the distribution feeder or to handle an outage? How do we handle that? This is one of those things where the programming detail can become very complex. And what is the impact of forecasting on the security, the energy, the ancillary service, energy imbalance, transactive, and demand response. That is, if the error moves from 5% to 10% accuracy, what is the amount of financial difference, if you will, degradation? How much do we expect these other applications to give us different answers and therefore different financial outcomes? This is one of the areas when you get into competitive markets as an ISO or a regional pool operator, reliability operator, where you really want to know what the forecast is telling you. Of course, today, the main thing that's coming forward is the interaction of fuel markets and electric markets. In the previous research I've done, I have often networked the fuel markets to the electric markets, primarily because the key idea, one of the key good ideas that Enron came up with, is that the best place to put a gas turbine is at any point in the gas network where there's a surplus of natural gas and a close by transmission network connection, essentially short-circuiting and removing contingencies or congestion from one network to the other. Or the inappropriate use, of course, is to reverse it and cause congestion by the application of gas turbine scheduling to increase the price of the markets. So this is one of the areas I looked into a while back to identify what is the anticipated financial impact of tying these two markets together. One of the interesting things, of course, is the spark gap contract traded on exchanges. Since natural gas is a primary resource for electric energy, knowing the price of natural gas will determine what the price of electricity will be, especially when the natural gas units are the units that are the clearing price in the markets. If we go to futures markets, those, of course, are very critical as they fold into the midterm operational planning of the next 18 months in terms of what electric energy is going to be available, what natural gas will be available, oil, coal, nuclear, hydro, and what will the demand be over the next 18 months? Will it be increasing or decreasing, or will it be shifting from one area that is growing from another area that is contracting? For example, the city of Detroit uses far less electricity today than it did at the height of the automobile industry in Detroit. And various cities on the West Coast have found that their electric demand has risen faster than expected because of their plans to entice companies to move there. Portland, Oregon is one of them. Seattle has been one where the demand increased dramatically. And these are things we have to keep in mind as we look at the mid to long-term processes. So this is the introduction to forecasting. The text has far more discussions of the applications that require good forecast. And we unfortunately will not have time to touch on wind or solar forecasting, which is so very critical when we're going to integrate the renewable energy, solar, wind, and even biofuels into the overall process of providing electric energy for the customers to help the economy, to provide comfort and security to our customers, as well as to profit from our ability to do a better job than we have done in the past. So that's what we'll be covering in the next couple of lectures. And we will go on with the next topic, starting off with the more traditional methods of forecasting.